All of the nonmetals on your periodic table have their electronegativities listed. For this reason, you would never have to memorize the pattern of electronegativity. You could just look at a row, you could look at a column, and you could figure out what the pattern was. Basically, electronegativity increases as you go across the table and decreases as you go down. But of course, this video is about the explanations. Why does the trend change in this pattern? Well, we've already talked about what the explanations are when we discussed atomic radius. Pretty much the same explanations work for electronegativity as well. So going across the table, why would atoms get better and better able to attract electrons as you move across the table? Well, consider that electrons, of course, are negatively charged. What sort of charge would attract a negative charge? Well, namely an opposite charge, a positive charge. And the source of attraction for negative charges in an atom is definitely the nucleus, the nuclear positive nucleus. So sodium has 11 protons in its nucleus, but chlorine has 17. So the chlorine nucleus is more nuclear positive. That means that the chlorine nucleus is better able to attract electrons, which explains why it has such a higher electronegativity. Now, you don't have the electronegativity for sodium on your chart, but I can tell you that it's approximately 0.9, and the electronegativity of chlorine is 3.0. So you can see that chlorine is a much better attractor of electrons. And of course it is, because its nucleus is so much more nuclear positive because it contains more positively charged protons, and that exerts a greater attraction on negatively charged electrons. But how do we explain that electronegativity decreases as you go down the table? Because what we know is that more protons makes the nucleus more nuclear positive. So when we look at cesium here with 55 protons, this thing has a very, very, very positive nucleus, and you would think is very able to attract electrons. Well, the nucleus is able to attract electrons, but that doesn't mean that electrons end up in the cloud of cesium, because the electrons are always going to be deposited in the outermost shell. And the problem is that that shell is just so far away from the nucleus. So even though you have a very strong nucleus, it's just so far away from where it's going to attract electrons. It's like having a pair of very strong magnets. If you separate these magnets by a large distance, you really can't feel any attraction between the magnets at all. If you had a pair of weak magnets, but you brought them very close together, you would feel the attraction between them. And the same thing happens here. So here you have sort of a mismatch, right? If you were to use the fact that the nucleus here is very strong, that would lead to you saying, well, I think this is a highly electronegative atom. If you considered the fact that the distance in which you're going to be attracting electrons, that's over 6 energy levels, that would say that there's going to be very little attraction. So which of these two features should you use to determine the answer? Well, again, you don't have the electronegativity, but I can tell you that cesium is approximately 0.7. It's less than sodium. And this reveals which is the more important feature. Basically, that if it comes down to strength versus distance, distance is always your best bet to use to figure out how the atom's going to behave. The fact that these electrons are going to be deposited or attracted to a location very far away from the nucleus, very far away from that attractive source for the electrons, it's just not going to be very good at attracting these electrons, and distance is the feature that reveals that. Now there's another way to make this argument, and that is to invoke the shielding effect. And the shielding effect basically says that that attractive force that emanates from the nucleus, that attractive force has to penetrate through all these layers of electrons. And every time it does, it gets weaker and weaker and weaker until eventually, by the time you get out to the last shell, there's very little attractive force left. And that explains why the electronegativity is so low. But here's another way of looking at this. Let's say that we were in the classroom, and this is me, let's say. So there's the short hair. And let's say that I had a flashlight in my hand, and I turned the flashlight on, and I was going to shine the flashlight at the wall of the classroom. What we would expect to see is a circular disc of light on the wall. Well, if I were to take a sheet of tissue paper and hang that in the beam, light would go through the tissue paper. You would still see a disc of light on the wall, but it would be dimmer because, of course, some of the light would have been absorbed by the tissue paper. And then we hang another sheet of tissue paper in the beam of the flashlight. Same thing, some of the light gets absorbed and the disc of light on the wall is dimmer still. And then maybe we take one last sheet of tissue paper, some of the light gets absorbed there, and now the brightness of the disk of light on the wall is very dim. In fact, it's barely perceptible. So what's happening is that the light is coming out of the flashlight, and every time it penetrates through one of those layers of tissue paper, it's getting dimmer and dimmer and dimmer until eventually there's almost no light ending up on the wall. And basically, the tissue paper is shielding the light from hitting the wall. It's an example of the shielding effect. So the shielding effect explains why large, highly nuclear positive atoms might actually have a low electronegativity and a poor ability to attract electrons.